Assalamualaikum and a very good day. My name is Farah Aina binti Azhar and today I'll be giving a presentation on my final year project with the title of Failure Mode and Fire Investigation on PV Solar Systems using FMEA and Experimental Simulation on Heated PV Component. So in this presentation, I'll be giving a brief introduction, background of study, objectives, literature review, methodology, results and discussion, and conclusion and recommendations. So I am really passionate about this topic because solar energy is one of the most famous methods of harnessing energy utilizing renewable resources. And developed nations have been incorporating renewable energy into their daily generation of energy since the early 2010s. Since the utilization of PV system is more widespread in these countries, more PV-related fires had been reported. With the high quantities of installations of PV system and generation of energy in Malaysia, we could expect that the frequency of PV fires would also increase in the years to come. Studies involving fire risk assessment of PV fires had been done in countries such as England, Italy, and Germany, but unfortunately, little to no study had been published on the PV fire assessment in Malaysia, despite the high concern of safety involving PV systems in Malaysia. More users would report on PV fires compared to if the number of users is very few. Thus, it has come to the attention of the government to do research on PV system safety to further clarify about PV-related fires. So the objectives that had been set for this research are to identify the mechanism of potential PV system failure that could lead to PV fires and to conduct an experimental examination on heated components of PV system. So these are the literature review on the common PV system failure modes. So the PV system failure mode of components could be separated into four main topics. The first one is PV module, second one is inverter, the third one is connector and wires, as well as others. So simply, how electrical fires are established. So for an electrical fire to be established, first we need a failure mode to occur. Any failure mode that could lead to electrical arcing. So the high temperature of this electrical arc could cause the combustion of surrounding insulations, such as if there is wood nearby, or for wires, if the electrical arcing occurs in a wire, the insulation could be easily combusted. So the combustion of this surrounding insulation could lead to the establishment of fires in these PV systems. So now I'm going to go into the research methodology. So the research is done in two different parts to satisfy the objectives that had been set. So the first part involves risk assessment of PV system. The risk assessment of PV system is done by using failure mode and effects analysis, or FMEA, so that we can assess the possible sources of faults in the PV system. And the second part of this project involves experimental examination on heated PV component. This is the project flow. The blue boxes indicates the project flow for FMEA, while the green boxes indicate the project flow for experimental examination. So for failure modes effects analysis study, or FMEA, it is done in conjunction to literature review as well as a survey, and it is done as risk assessment method for PV system to assess the possible sources of faults. As mentioned earlier, we have PV module, inverter, connector, and wires, as well as other failure modes. And for each of the failure modes, we assess what are the causes, failure modes, as well as the effects, as well as we assign a severity ranking, occurrence rating, as well as detection rating. So for the severity, occurrence, as well as detection rating, we can multiply the numbers and to get the risk priority number. So each of these points represent a failure mode. Once I compiled all of the failure modes, what I did was I construct this survey using Google Forms, and I disseminate the survey to PV companies that are listed by SEDA to gain their opinion on the failure mode that they have encountered in the field. Once I obtain back the data, I basically construct the FMEA table and I assign 3 different ratings for each of the failure mode. So 3 different probabilities are rated from 1 to 5 for each of the failure mode, and I multiply the 3 individual criteria to get the risk priority number, or the RPN. A threshold limit is set whereby the values above the limit is considered critical and requires countermeasure. So the threshold limit value is 63. Now I'm going to explain on the experimental examination. So the experimental examination on heated PV components is done to understand the mechanism of failure mode of PV system. Here, I want to study the effects of internal resistive heating of wires on the performance of PV module. So a study done by Smith on the recognition of fires originating from PV solar system. Basically, he studied fire scene evidences and found that in every case there is evidence of electrical arcing having occurred in the vicinity of DC isolators. So I want to simulate this study, but instead of using DC isolators, I use PV module. So this is a brief flowchart of the experimental simulation. This is the setup of the experiment. We have a PV module and one of the wires is supplied with heat from a Bunsen burner, and the thermometer reads the temperature of both of the wires. Other than that, we also have another experiment that is done by a postgraduate student, whereby the fumes produced from the process is collected to be analyzed. This is the setup of the experiment. We have the PV module, the heat source, and one of the wires is being supplied with the heat. And this is the setup with the temperature reading.
Now for the results.
So this is the FME table that I had constructed from the literature review as well as from the survey. So as you can see here, this is the FME for the solar PV module. We have the causes, the potential failure mode, as well as the effect of the failure, and the severity, occurrence, as well as detection ratings for each of the failure mode, as well as the RPN number that is obtained by multiplying the three different values. So this is for the solar PV module. This is for the inverter, as well as connector and wire failures, and other failure modes. So I cannot explain in detail each of the failure mode, so I'm going to summarize the whole FME table right here. So from the FME study, I find that the failure mode with the highest RPN number is the control board failure in inverters. So the reason why the RPN number is really high for this failure mode is because it is contributed by the high frequency of occurrence. So the severity of the failure mode is not that high, but it occurs very frequently in inverter systems. So therefore manufacturers need to take action and improve the quality and manufacturing of these inverters. And other than that, poor wire connection comes in second with a value of 40. So the reason why RPN number for poor wire connection is really high is because of the severe effects of the failure mode. So if there is a poor wire connection, there is a probability of establishment of fire. But fortunately, none of the RPN of these failure modes exceed the threshold limit of value of 63. So none of this is too severe that immediate action needs to be taken. So now I'm going to go into the experimental results. So this is the FMEA that I've done before, and as you can see here, for PV solar module, a lot of the failure modes have relatively high RPN, such as burn marks on panels, cell cracks, hot spots, as well as this is for wire failure, poor connection. So the reason why I highlight this is because these are the failures that I want to try to simulate inside of the experiment. I cannot simulate burn marks, cell cracks, hot spot, but I can simulate the effects that is caused by this failure mode. All of these failure mode have similar effects, which are really severe effects, such as electrical arcs, fire, overheating of cells, total power loss, as well as heating of wire again, and electrical arcing. So I want to simulate this inside of the experiment. So expectation for this experiment, I expect that the solder joint will fail due to resistive heating of wires, and the bypass diode will experience thermal fatigue from the continuous heating, and the PV module will not be able to operate since the solder joint failure caused by the resistive heating will cause an open circuit. But this is what I expect. But after the experiment, I find that the heat conducted by the wire is not hot enough to cause solder failure within 2 hours of the experiment, and the bypass diode need constant thermal stress for it to be damaged. And the PV module was still functioning well after the experimentation, and no open circuit is detected. So before the experiment, I tested the performance of the PV module, and we get an output voltage of 21.5 and a current of 2.32. And after the experiment, I expect that we cannot produce any voltage and current, but instead we managed to produce a voltage of 20.4 and current of 2.17 ampere because the PV module was still functioning well even after the experiment. So this is the image of the wires. So basically, I apply heat to the wire, the conductor part, to simulate internal resistive heating. So the heat should be conducted through the wire. And after the experiment, we find that the copper conductor is damaged and there is a formation of white substances as well as embrittlement of wire. So this serves as a post-fire indicator, like if at a fire scene you see these kind of indicators, that means there may have been an internal resistive heating or a fire nearby of the wires. So here we have the image of the junction box here, as well as the bypass diode right here and the solder connections. So I expect the heat will be conducted through the wire and cause solder point failure. But after the experiment, we see no changes in the bypass diode because it remains undamaged and the solder connections are still intact. Results: a common 60S and 40 PB solder joint has a solidus temperature of 183 and a liquidus temperature of 188 degrees Celsius. So therefore, the temperature needs to reach above 183 degrees Celsius at the solder connection right here for it to be able to immediately melt the solder connection and thus breaking the connection altogether. So therefore, if we want to simulate, what I'm trying to simulate here is the temperature needs to reach above 183 at the solder connection right here for it to be able to immediately melt the solder connection and thus breaking the connection altogether. So after conducting the studies, here are the recommendations that I can give. So first is that the FMEA study can be done by including more components such as the switches, batteries, as well as the relays. And the FMEA study could be conducted in further detail on a more specific type of PV system, which are mostly demanded in Malaysia. And more experimentations on real-life simulation of failure modes could also be conducted to improve the understanding on how the failure mechanism occur and how to prevent them. So in conclusion, the study on failure modes of PV system is very important for us to increase the understanding of the events that could cause the failure mode and the effects of these failure modes in a typical PV system. So that is all for me, and thank you for watching.